Hello. Before I let the recording of the talk play, I want to thank my friend Dima for writing a substantial portion of the Python code I use in this talk. I wish I had remembered to thank him in the actual talk, but oh well. Here's the talk. Please sign up with this thing if you did. I guess you can't chase. But why did I say 1330? God, it's been wrong the whole time. Is it? Hang on. No, yeah, no. Is it, do I have the time of it wrong? I don't think so.
It's 12:30.
Yeah.
Yeah, I saw your thing that said 13:30, and then I saw that so I was like, I had to fill it out to get the room reserved. I was like, wait a minute, did I reserve the wrong time? I reserved it for 12:30.
Oh, thanks. Wait, you reserved this room?
Yeah.
Oh, okay. Cool. Um,
You just had to spend a few minutes. I was like, did I reserve it wrong?
right. No worries. So yeah, this will be kind of informal because I didn't prep quite as much as I'd liked, but I think that's okay. I'll be adapting from this this blog post because I think the ideas in it are really neat. And the simple notion, I guess, maybe I'm going to be doing more writing on the whiteboard than usual because I don't have a lot of material. Where I have a marker. Okay. So how familiar are you with concurrency in general? A bit. Not at all. Okay. So you've written some code though, right? Okay. So the most obvious thing people think of with concurrency is threads, which are things within your program that can run at the same time. So typically, your program is only running one function at a time, and it just steps through the code one after the other. And then, one second. Okay. Steps through the code one after another. And it just runs, one line after the other, right? But if you spawn a new thread, that's a thing that your program can do, and it can say, okay, run this function at the same time as the rest of the code I'm running. And there are a couple of reasons why you might want to. Are you here for the presentation?
Yep.
Oh, awesome. I'm just starting, so you didn't really miss anything. But I will show the slide. One second. I'm sorry. Here you go. You probably don't even see that, but some people might, so that's for them, I guess. But the first thing I want to talk about is why the hell we even use concurrency. So by concurrency, for now, we can just be thinking about threads. Does anyone have any ideas why we might use concurrency? Just in general.
It's faster.
Okay, to make things faster. So how would that work, I guess? Say more.
Well, if you have a certain task that maybe has a lot of parallel concurrency to doing those calculations all at once or somewhere at the same time?
So this idea is like the main reason why we think of using threads is we wrote our program, or we want to write our program such that it can use multiple cores, basically. And when it comes to threads, we really are just talking about using the parallelism in our CPU between different cores. So we want to use our program so it can use multiple cores. The reason why we'd be doing this is if our algorithm is something that we can split up into something that, multiple bits of it can happen at the same time, right? So if we're like rendering a scene in a video game, if we're rendering a scene, let's think of it this way. If we're rendering a scene for like a movie, and we're doing that on the CPU, that's pretty easy to split up, right? An animated movie. You can render the left half at the same time you're rendering the right half, and they don't really depend on each other. The code that's working on the left half just needs to know about whatever's on the left half of the screen, like the objects, and then it turns that into the pixels on the screen. And you can split that up, way more. So I'll say this is for parallelism, which I don't know how to spell, but that doesn't matter. These terms are slightly different. The article, I think, has a really good way of describing it, which is concurrency is really about what you have to think about when you're writing your code to figure out if it's correct, right? So if I have multiple threads, I'll bring this up. Okay. macOS is having a wonderful macOS moment and doesn't want to get rid of this window. So I'll put it down here. The article says that concurrency is about how you write programs and parallelism is about how you execute programs. And I think that's roughly a good way of thinking of it. Parallelism is when the things are actually happening at the exact same time, like handled by different pieces of hardware, usually. I think always. But concurrency is how we were thinking about writing it. So concurrency is like when you use threads or when you use something like async await in JavaScript, that's also a form of concurrency. You have to be thinking about, okay, these things could be happening at the same time, right? You have all the correctness problems as soon as you go concurrent. But you don't actually have any of the speed up until you go parallel. So if I have like 50 threads and then I run my code on a CPU with 8 cores, like at most 8 of those threads are going to be actually running at the same time. So at most I'll get an 8x speed up. And because threads involve some overhead to start them and some overhead to switch between them, I probably won't get an 8x speed up, right? And I would be better served in that case by having 8 threads, 1 per core, and then there wouldn't really be much switching between them going on. You just keep running the 8 threads. Okay, but there are some other reasons why we might want to use concurrency. Does anyone have another common reason for why we might want to use concurrency? Like it's like this covers like maybe 80% of the cases where it's like, oh, I need threads, right? I need threads to make something faster. I don't know about that. It covers a lot of the cases, but
yeah, maybe to write clean programs.
Maybe, right. But I think that's maybe that I'm gonna put that as number 3 because that's what this is about, and I think that's cool, but it's not at all obvious to me. Maybe this one is the trickiest one to think about. Have you taken 342? Okay, and that's perfectly fine. 342 is like you write some graphical apps in Java, and then near the very end, you touch some threading. But the goal is not to speed anything up. In fact, all you're doing is you're running a sequential algorithm on one thread that is like solving a maze for you. And it's a graphical app, so the idea is this thing might take a while. We want to do it in the background and then show the user the result. Like, we want them to be able to say, start doing the expensive thing, and then it happens, and they can still click around and do other stuff. And then at a certain point, like, a button becomes not grayed out and is like, show me the result of the expensive thing because the thread finished. So there, we would want to use threads even if we just had one core, because the point there is we're doing something expensive. But what is it? We're doing something expensive. It's not that we need to be doing two things at once. It's that we need not to prevent the user from doing other things. We need them to still be able to click around. And that maybe the unintuitive thing here is that in order for them to be able to click around, our main UI code needs to still be able to run. So we can't just like say, that everything that our program is doing is just doing this expensive thing. There need to be two parts of it running at the same time. So I'll say this is like our problem, not our problem, our Our solution has parts that progress independently, right? Like, fundamentally, we don't care about, not only do we not care about what order these things run in, right? Or like what's running at the same time between the expensive thing and what they look at, it's that we need both of them to seem to happen at once. So we need them to be at least simulated to be concurrent. We don't need the parallelism. We could do that on a one core machine, and what would happen there is that the operating system would be switching between the expensive thing and the UI as necessary. But this make clean programs is, I think, like I'm sure it has overlap with this. Like, you could say, well, this code gets cleaner and faster, or this code gets cleaner and is able to progress more independently. But the examples I'll be talking about here actually don't progress independently. Like the code that we're thinking about here will be really weird multi-threaded code. Usually, what you're doing in multi-threaded code in both of these cases is you want your threads to be able to work as separately as possible. Here, they will be achieving the same task. So some of this will just be me explaining, but also me answering questions about code examples. Here, I wish I had finished like translating this. Let's see. I think some of this is Go code, which you're probably not familiar with. And my goal had been to translate it. The complicated bit I will have in Python, so that'll be nicer. Does anyone have an eraser? Yeah, for this. Oh. No. Not at all. This looks like it, yeah. I might as well have another marker too. So I think this code is readable enough, even if you don't know too much Go. The idea is we have this variable state, and first I'll describe what problem we're trying to solve. We're trying to solve matching this regular expression. We're trying to solve figuring out whether this thing is like a quote or not. So, this is not a quote, a quoted string, right? This is a string. This isn't, right? Also, I think in this definition, like, this is a string because we say that it's a double quote followed by anything that isn't a double quote or a backslash, or a backslash. These two backslashes are one, followed by some character. So, and then that thing many times over, and then a closing double quote. So the inside can't have a double quote in it, of course, because then it would close something. But this does allow us to do something. I guess this is more useful to explain why the hell we did this. Maybe I'm being sarcastic about the notion that we're greeting the world. So I wanted world to be actually in double quotes in my string. So this way, these don't close anything, because this is allowed to be that double quote. But the point here is that this is some weird ass code that is like reading from wherever we're getting the string, one character at a time, and it's figuring out whether it's a whether it's a quote or not, right? So I'm not sure if I'm going to get through all of this. I think I'm not going to, but I'm just going to try to give it a sense of why this code makes some amount of sense. We have a state here, and that variable just holds like some number as to what part of the regular expression we're in. So the notion is we start out in state 0. So the first character we see, if it's not a double quote, we know it's not, it's string. But if it is, implicitly we got here, so it is, then we go into state 1. So the next character we see, we end up here. If it is a double quote, we return true. That's just like double quote, double quote. If it's a backslash, then we go into state 2. So in state 2, this seems kind of silly, but what happened here is we did read another character because we went around the loop again. This is a while true loop. That's how you write it and go. So this is just going to keep looping. So the point is, we saw a backslash, and then we ended up here, and we completely discard that next character. We just go back to state 1, and now we're reading the character after that, like we're reading capital W or something like that, right? Have you guys taken 301? Or do you have a sense of like finite automata or regular expressions or anything like that? So this is the reason why this code kind of corresponds to the regular expression is that regular expressions and finite automata, which is this notion of a machine that transitions between some states, are very similar to each other. You can make a finite automaton that mimics any regular expression, that can recognize things that match the regular expression and discard things that don't. So you can imagine saying we have 3 states, 0, 1, and 2, and well, there's a way to get from state 0 to state 1, like if C is not a double quote, I guess. And there are a bunch of other ways to get between these states as well. So that you might have written the regular expression and then turned it into these are the states, right? And then written this code. But I would argue, and he argues as well, that this code is god-awful ugly and not pleasant to look at. It has some advantages over what we might want to do, but he spends the rest of the article, or not the rest of it, a lot of the article describing slowly how he turns it into, are you here for the event? Or no. It's fine. You can still be here. I was just curious. Describing how you can turn this code into code that looks a lot nicer by, instead of recording this state variable, just going from one part of the program to the next. I think at first I'll show the final bit and just try to convince you that it does the same thing. So this is how he would say, let's see. Yeah, this is how he would say, let's write the code a little nicer without that state variable. He would say, okay, what we really care about is just like the first part of the string. We don't need to have any state variable or whatever. We know that if that's not a double quote, it's not a quoted string, right? And then we just have this loop that is, as this is like a while c is not equal to double quote, read, get the next character, and if c was a backslash, then read again and discard the next character. So, and eventually, c will be a double quote, and we fall out of this, and that's the final double quote, so we return true. So do you see how this sort of matches what the other code does? At least roughly, it does.
What?
Yeah, I mean, instead of cases, it's just
Yeah. Sorry, what? Instead of.
like the previous one had cases now.
Yeah.
Like this doesn't. So it kind of matches.
Right.
And I would say that this code is a lot nicer, to just look at, because I understand, whenever I'm reading code, I understand that part of what impacts what this code does is where I am in the program, right? I don't have to constantly, when I get new information, I don't have to immediately put it in a variable. If it's just that the new information is, I can go to the next line. So that's the key intuition of this article, is that our position in the the line that we will next execute stores something helpful to remember in our algorithm. The next intuition is there are reasons why we don't always get to write this code, and one of the reasons, I think, so I'll do this, and then I'll revisit what that transition really was. So far we're just going through two ways of writing a program that parses a string that may or may not be quoted, that returns true on these things, but false on this sort of thing. And this is maybe a relatively simple example of that. But if we had written everything using, if we had started with the regular expression and then turned it into a finite automaton of some sort, we might have ended up with this code that would have switched based on some state variable that would represent which state we're currently in, right? So this is kind of ugly in my view and in his view. But then we eventually transformed it into this. But I want to get to the key bit first, which is let's see. This is, I think, the probably most important sentence that I haven't talked about yet. Before we had threads in most languages, we actually had to do the business of having something like a state variable that would be kind of awkward. And the reason was sometimes we fed.
What? It's the pressing sensor, so if you hand over it, it'll turn off the laser.
Can we turn that off? Okay.
You just stand it on the side and then gesture.
Yeah. Imagine. So we definitely aren't trying to make our program faster. And our program is still like a thing that just doesn't really support, it's not really about like multiple completely independent things happening. But let's say that what we're doing is we're taking in base 64 input. Is anyone not familiar with base 64 input? I can briefly describe it. It's not like the prettiest thing in the world. But what? Yeah. So base 64 is an encoding of like any data that you can imagine into strings that consist only of certain characters. There are only 64 characters in the alphabet. So frequently, this is used to take arbitrary data. Like, say you want to upload a file, and for some reason, the pipe through which you're uploading the file can only support characters in like that are human typable text, right? Like alphanumeric characters, plus maybe some punctuation. I think I don't know everything that goes into base 64, but oh boy, oh boy. What a word here. That just means like 64. But basically, this is about, we can encode any value into a base 64 number first, and then the way we do that is like, if you think about our value as being some series of bytes, right? It's fundamentally a base 256 value, because each byte could have any one of 256 values. When we want to turn it into base 64, we first have to just convert the number into something base 64, and then based on which value of each digit, we pick one of these characters. And then our text gets longer, but we can fit it more places. If there's like a special meaning to some character that isn't one of these, you know, if there's a special meaning to, I think backslash is not one of these characters. And we're not allowed to use that in the place where we're sending our data, it's fine because we made sure that our data doesn't have any backslashes in it. It only has these characters. And then on the other end, they can get the original data back out. So the tricky thing about this is that it doesn't exactly match like the number of digits needed as our original byte stream would have it. Let's see if I can make that make more sense. Right. When you're decoding, so it starts as base 64. When you're decoding 4 base 64 letters, right, those characters, you get 3 bytes out because each character encodes less information in base 64. Does that kind of make sense? It's like numbers are longer in octal than in hexadecimal. It's the same intuition. And this is really awkward because what we want to do is what we want to do with our code that was recognizing this is we want to process 1 byte at a time. So that's like one of these bytes. And then, but like, if we have the base 64 stream and we want to make sure that we don't just decode it all in memory, say it's really big, right? Then what we need to do is we have this problem where we have some part of the code that is decoding it from base 64, 4 characters at a time, giving us 3 bytes. And that would be simple to write. And then we have our code that was dealing with 1 character at a time. There's just this mismatch. It's not obvious how to feed this code 1 byte at a time. Because when this code reads a value, a byte, it's then, like, we need to be still running it, like, for it to be able to read more bytes. So let's imagine that we read these 4 bytes, and then we decode them into 3 bytes, right? Let's say those 3 bytes are the 3 bytes here. If we ignore this code for now, let's say we were writing code that just like read 3 bytes in, and then read 4 bytes in, and then turned them into these 3 bytes, and then we tried to run parse quoted on that. We haven't read the whole thing, so we've just read these 3 bytes, and then we run parse quoted, and parse quoted sees the opening double quote, and it says, okay, we're fine. And then it sees that the next thing is not a double quote, so it reads a character. And then, but it's still not a backslash, so it reads another character. And then we're here, right? Our function isn't going to return at this point. It depends on exactly how we set it up, how we fed it this read function or whatever. But what we need to do now is decode the next 4 bytes and then hand it those. So this is why we might have used this state version. If we had the state version, it's actually pretty simple to do exactly what we're doing. We read 4 bytes, we turned them into 3, and you'll see here that the only place where we read is up here. So we can actually replace this read with just like take a parameter of the byte to process and make this state not a local variable, put it on, make it a global variable, right? So then this is all a function, and we run it on 1 byte at a time. So we just run it on the first byte, the second byte, the third byte, and then at that point, state is wherever it needs to be to understand the next byte and to get to the next part of the string. So the beautiful thing about this program is that it looks exactly like, you know, what our code that manages the decoding really should look like. It just gets 4 characters from the underlying base 64, and then it splits it up into 3 characters, and then it hands those off, right? But the tricky thing is, it's like, in order to do this, we have to be able to pause. In order to do this and use the nice version of parse quoted, this one, we need to be able to pause parse quoted and resume it. And we need to be able to pause our decode function and resume it, because they won't be moving in lockstep. This one wants really the whole quote at once, but decode is going to be producing 4 bytes at a time. So this is what concurrency is actually about. Concurrency, you might be thinking of it as these things run at the same time, and it's true, but the real like value add as a programmer is that it lets us pause and resume functions at arbitrary times. That's like the thing that you need to be able to simulate this. To be able to use control flow, use the position within the program to record where you are. Right. So I think he went here. He didn't make it a global, but he put it on a struct, which the syntax is funky, but it's a struct. And then this was a way to make it work, where the parser, this struct has a write method, and it sets this variable on that on an instance of that struct, and this means that we can call this write method, and it only handles 1 byte at a time. So our read code, so we can use this bit of code where all of this is very nice and clean. I think there is a way that you could turn this into something that also has states where it's like, oh, like what stage, how many bytes have I read here? You know, am I 3 bytes into the next 4 byte chunk or something like that? But he doesn't go into that, and that's fine, I think. So then, let's say that instead, let's skip that business. This is very go-ast code. I think I'm going to try first just getting through just like 1 or 2 of these. Actually, no, I think that's very boring. Let's see. So there's going to be sort of a break in this code where in this presentation where I jump into Python because I've actually written some of this stuff in Python and also jump to a different problem, I guess. But this different problem is the one that he gets to near the end. And it is this notion of we have 2 binary trees, and we want to see if they hold the same values. Who here is not familiar with the notion of a binary tree? Who here is familiar with the notion of a binary tree? Brilliant. Okay, so importantly, we don't care whether the binary trees have exactly the same shape. Like one of them could have all the values on the left, right? And then its right child has no children or something like that. And the other one could be completely different, could be balanced, could be all right heavy or whatever. But as long as it has the same values in the same order, like going in order traversal, then we want to consider them the same. So in this lovely Python code, we have this sort of example where we're just defining a class node, and it just has a left and a right and a value. And we consider that node, like an instance of this node, to be a tree. We don't have a separate tree class because we don't really need one. And this is just a really basic tree, I think, just to give you a sense of how you would use this. We have a node with a left child. So I'll just draw this out so we have an example tree. Imagine that. Its left child has no children, but it has the value 1. I think this top node value is 5. And then we have, no. This left node has a left child that has the value 1. It's more interesting, actually. And a right child that has the value 4. And its value is 3. And then our right child of the parent has a left child with a value 6 and a right child with a value 10. And its value is also 3? No, 8. Doesn't really matter. But okay, so we have a binary tree. And we want to be able to check if 2 of them have the same value. So the point of this code is, let's start with something simpler here. Actually, I'm going to live code this. I think that might be interesting, though it might also be incredibly an awful idea. But let's see. How would we start by, let's start by just traversing the tree. How would we start by traversing the tree? Let's say we want to print all of the values in the tree.
So that you would go to every node and here unless we get a node is equals to null pointer, we would keep calling recursively on left and right side.
Okay, I think the important part is we call recursively on the left and the right.
Yeah,
right?
left and right.
Yeah, and as soon as we reach null, then we're done.
Yeah.
So far, we don't actually have a way to just loop through it, unfortunately, because we haven't written an iterator for it. I showed an iterator there, but we don't have an iterator. So let's just say print all, and we take like a node, which I'll call tree, because that's the point of it. And then what's the, so at some point we're going to print this node's value, right? What's the first thing we do before that?
Like check if the root is equals to null pointer.
Okay, yes, true. If the tree is none, we return. That's the same as the null pointer check, just in Python. But first, because we're trying to do this in order, we want to print, 1, 3, 4, 5, 6, 8, 10, right?
Okay, in order, then first
Yeah.
one left, then
Yes.
print and then right.
Yes, so we want to print all the ones in the left, and then print the one in the middle, and then print all on the right. I have no idea what happened in my editor there. I think I probably accidentally touched the trackpad or something. So yeah, this is exactly what we want to do. The issue is when, I guess the important thing is we could replace this print with anything. And we can do anything to each of these values in order, and that's easy. And we could do that in part by taking a function and instead, running that function on the value, and then passing that function down whenever we call ourselves recursively, so we're doing the same thing on all of our subtrees. So now this is like process all. It's not just for printing. But the issue comes when we want to do this on 2 trees at once. It's really tricky to take this code and just turn it straight into something that works on 1 tree and another tree and checks if they're the same. What we want here is an iterator. We want a way to reach at 1 tree, and get the next value in it, and then reach from the other tree and get the next value. And the point of the iterator is to remember where we are in the tree. So then we can ask it next, after that, and it gets the next value. Because here, I've committed to processing the whole tree at once. But what I want to do is process the 2 trees in lockstep, right? Of course, there are other ways of solving this problem. The simplest way would just be look at 1 tree, dump all its values into an array, look at the other tree, dump all its values into an array, compare the arrays, right? We have completely solved the problem, but now our solution isn't streaming. Our solution is, what I mean by our solution being streaming is we don't need to copy all the state. We don't need to copy all of the trees, I should say. And that means that we have a lower memory footprint, and we can finish earlier, right? If the first 2 values in the 2 different trees are different, we can just like short circuit and be like, nah, they're different, right? Whereas if we were first copying them all into an array, we would take the same amount of time. We would be copying, like, take the same amount of time for that case, or much more time for that case than we really need to, because first we have to copy everything, right? Okay. So the point of this iterator is just to show that writing the iterator is non-trivial, right? In order to write an iterator through a binary tree, we need a stack to figure out where we are so we can go back up. Nodes in the binary tree don't have links to their parent. And I'm not even sure if that would fully solve the problem, but they certainly don't. So when we're at 1, we need to be able to go back to 3 so that we can visit its right child. So this iterator has a stack that is just an array, and then the first thing it does is it pushes the entire left spine, so that's these things, until like it hits a left child that has no left child. And then whenever we want to go to the next element in the array, if the stack is empty, we say there's nothing more, and this false, we're returning 2 things at once. False just means like the iterator is done. When we returned an item, we return true in that position. But if the stack is not empty, then we pop something off the top of the stack. So initially our stack is something like so then we pop something off the top of the stack and we return that. But before we actually return that, before we actually return this 1, we push the right child's left spine, which means in this case, there's nothing to it. But we go to our right child here, and then we push whatever's on its left. So really all we end up pushing is the right child itself. And then the next time we call, next, we still have something in the stack. So we pop the top of the stack, we return 4. Wait, no, we don't. Hang on. Can't be doing that. We need to return 3. Let me think. Well, T is not none. Well, as you can see, the point is this code is kind of non-trivial to write. I actually think I'm not going to be able to debug it at this point, but there is some logic to this. I think maybe we need to not push 4 quite yet, or something like that. But what we need to do is obviously end up returning 3. And something I want to connect this to is if you've taken 251, frequently the end of 251 has you writing a binary tree class in C++, and it's a real pain because you need to write an iterator for it as well, right? It would be great if there were some way that we could avoid writing all of this code. But it is very nice to use. And then it's pretty easy to imagine writing code that checks if, like with this iterator, that just fails fast and checks if all the items are the same. And it doesn't care about if the trees are shaped the same because it's separately keeping track of where it is in each tree. All the iterator gives us is just the values. So the real point is we don't need that iterator. If we have threads, then we could write code that looks a lot like our print thing or our process all thing. And that's basically this function. I think it's exactly the same as what I'd written up before. And then we can have a function that figures out if two trees have the same values with concurrency. And what this does is, I think let's start by just looking at the loop. It gets, these are just the values. Value from the first tree, value from the second tree. If they're not the same, return false. If they're both none, then we return true because we've gone through both trees. So obviously, if they're both none, they weren't. They were the same, but we don't keep going through, infinitely. We're done now. But how we got here is we actually ran the things that walk the tree, things that sort of process all the values in the tree on separate threads. We have this function tree walker that we define that just goes through everything in the tree, and for each value in it, it puts that value in a queue. And then at the end, it just puts none in the queue forever. So there's not really any point to it putting it there forever. It could just put it there once because we are only going to look at it once, but still nice, I guess. So where did it get this queue? We call it here, again in a lambda, and we say your queue is this queue to talk with thread 1, or this queue to talk with thread 2, and your tree is the tree that I'm telling this thread to process. So every time I get from this queue, it's the next value from tree 1. Every time I get from this queue, it's the next value from tree 2. And an important thing to note here is we're not getting any, we're not getting much real concurrency. These things are kind of happening in lockstep. I show that by making these queues max size 0, which means that it can actually only, it doesn't even hold a value. If this puts something in the queue, then that just means it's waiting until someone takes it out, right? The algorithm still works like that, but and this is slow. Usually, you might want to make a queue with an infinite max size or an arbitrarily large max size, so that one tree could be entirely processed, and then another tree could be processed independently, and then this code could also be running independently. But the real point is our algorithm is just as sequential. We only need to be doing one thing at once, but the reason why we're using the multiple threads is because it allows us to pause and resume this function. So I think honestly, that's basically all I have, and I'm barely over time. Does anyone have any questions, or I can just sort of wrap up? I know that was kind of fast, and I know that the iterator I didn't get to go through as much as I'd like, but yeah, they're created right here. So this thread is given one tree and one queue to talk with the main thread, and then this thread is given the other tree and a different queue to talk with the main thread, and they just put their values out there as the thing that they do with each value into that queue, and we read from that queue. We effectively use this queue like an iterator. The reason why this isn't the same as putting everything in the array, like just dumping it all into the array, is because this queue doesn't need to hold any more than, in some sense, 0 items at a time. It just needs to be a place that you can put something and then wait until someone else grabs it. But yeah. Yeah.
I guess is the queue I'm wondering if there's any like happens before.
Yes. So that's the queue in Python is thread safe, which means that this is totally fine to use. And I think, I'm sure that in Python that means that if you put something into the queue and you've done something before, anyone who reads that thing from the queue sees what you did before. So that concept from concurrency, fancier concurrency applies. So I guess to wrap up, I'll give some caveats. There are more caveats. Oh no, I'll. There's one more thing I want to say, which is the beauty of this is that this stack. Maybe I didn't particularly well describe why this stack is necessary, but I think if you did this as the assignment in 251, you will have seen the stack. This stack, which we were storing in an array variable here, still exists in our concurrent solution. And we still need one stack for each tree. It's just that now our stacks are literally the call stack. The call stack being, the where we are in which call of which function. Whenever our manual iterator would pop something off the stack, our for each value code would return, which is popping one thing off the call stack. Which means that here we're basically going all the way down the left, and then we're coming up one and then going to the right, then coming up two and then going to the right and then all the way to the left. That's what we're doing implicitly in this code, but I would argue that this code is way easier to read and way easier to say, yeah, this seems right, than that queue code, than that iterator code. Yeah, then the last thing I'll say is just bunch of caveats is we used threads when we didn't need to, like definitionally. Threads are scary. Anyone who's taken 454 or any, which is totally fine if you haven't, anyone who's touched threads knows that threads are scary. And that as soon as you use them, you might have weird bugs that you would never actually be thinking about having because they don't fit with our understanding of the world. I'm pretty sure this code is all right, but if you make a weird mistake in this code, the only time I'd recommend doing this is when you can spend enough time really thinking about this, and when your code is simple enough that it's like, no, I know what I'm doing here. Or if you have what is it? If you have a language that's a little bit nicer than Python or Go and has something called coroutines, which are actually the perfectly sized solution to this problem. Threads are nice, but threads are the right solution for basically these two problems. Really, it's the right solution for this problem. And that's because the whole point of threads is that they could be running on different cores. Otherwise, for complicated reasons I won't get into, there are more efficient ways of having these multiple flows through our program that we can switch between without talking to the operating system. If you want the multiple flows to actually run on different cores, we need threads because that's how we tell the operating system about these are multiple things that are running at once. But if we don't, it can be faster to do something like Python's async IO or JavaScript's async await and just use something single-threaded but have concurrency with within that single thread. It's beyond the scope of the talk, but that's why threads are really only perfect for this. Threads can certainly do both of these things, and they can do all three of these things. But here, we didn't actually want our code to be able to run independently particularly, right? We want our it is much simpler to think about our program. A lot fewer things can go wrong if actually all we do is we switch between running this bit to that bit, right? And that's one of the reasons why I said the queue has a max size of 0. I think the algorithm would work with any other size queue, but I wanted the code to end up doing the same thing as the sequential code. I didn't want it to be running ahead. I wanted it to be doing the same thing because the point was this solution only needs to record one item at a time, right? And we don't need to fill up these queues with all these items. In the worst case scenario, that would just be the copy it all into an array solution. But I actually was kind of fighting threads when I did that. It wasn't that ugly. All I had to do was max size equals 0. But if I hadn't, then like the natural tendency of threads is to just let them go hog wild, right? Go as far as they want. And that's where you get the problems. The problems are really because threads don't execute in lockstep at all, right? Threads can arbitrarily run, arbitrarily be switched between. And that's sort of scary to think about. Coroutines are available in Lua and probably like a few other languages, but Lua is the one that is most popular. So that's a sign for like, how likely are you able to use it? I don't know. But coroutines have you explicitly say in your code, I'm done running for a while, run something else. Which means that you don't have nearly as many shenanigans where threads are racing to do the same thing, and you actually can't have most of the bugs that you could have with threads. I think he talks about this in Coroutines for Go, where he talks about coroutines in Lua, and he uses the same example. I would really recommend this article to anyone who's more curious about like how to do this correctly. But I guess the last big issue, two more big issues. One, we introduced threads. That's scary for correctness. It's also slow. Like I was saying, threads are really only well suited for this because this is the only time we need them in order to run our code on multiple cores at the same time. And frequently we do these two things with, or we do this with other abstractions like async await or whatever. What was I thinking? So introducing threads where there's no hope of actually making things faster is basically guaranteed to make things significantly slower. The only advantage of the solution we wrote is that it doesn't need to hold all of that state compared to the solution where you just dump them into arrays. When it comes to this solution with the threads compared to the solution with the iterator, I haven't benchmarked it or anything, but I'm certain it's much slower. The other thing is, I'm not so sure how broadly applicable this technique is for making things simpler. It certainly works in this case, and I think it works in a lot of cases where your algorithm is recursive and you want to do it twice, and that's kind of common, but there are certainly cases that he describes here where it doesn't work so well. And I think it's really best suited for those recursive algorithms because that's where, like, whenever you have a recursive algorithm, you're implicitly storing a stack on the call stack, which means that if you were to try to have these two recursive algorithms run independently without concurrency, you would need two explicit stacks. So that is why it's really nice. That's why the concurrency lets us avoid the explicit stack by putting it on the call stack. I'm not sure if for non-recursive algorithms, it's as easy to take the state that would have been explicit and then make it implicit in our control flow. But I still think it's sometimes possible. And there are other, I guess the other big issue with our code is that at the end of this code, we've got 2 threads that are just sort of hanging out, even though we don't need them anymore because we never shut them down. We could have joined them. Actually, no, we couldn't join them. Joining them would ask them to run to completion, and they're never going to complete because they're just going to keep shoving none into this queue. So that's not the nicest thing. But I hope the point is that this was a good enough example of a concurrent algorithm that you can think through and that can make code look a lot more like the code that you would have wanted to write as opposed to code where you're fighting with something. The impetus for this talk was the hardest assignments that I've seen have been things like the non-blocking I/O HTTP server in 361, where you're using the select system call. Exactly the problem there is that because of that, you have to store the state of each transaction in some variable. You can't just store it in the implicit notion that I'm currently dealing with this transaction. So the real benefit of something nicer like threads or async await is that it lets me think about these separate tasks that I want to happen separately as separate tasks that I want to happen separately, as opposed to having to write the logic that switches between which one I'm handling on the fly. I don't know if that makes much sense. It probably mostly relates if you've taken 361. But that assignment is, that assignment is tricky. And the reason it is because you need to be able to put down your work with one client and pick up another in order to correctly execute on that, on the benefit of that task. Otherwise, you're going to get stuck dealing with one client. The whole point of that assignment is such that you're writing a single-threaded program, but you can deal with messages whenever they come in from anyone. In that case, you're serving HTTP requests wherever they come in from. And the ability to put it down requires you to put that stuff that you're putting down in a variable. And probably in a struct or in a global variable or something like that. Whereas if it were with threads, you don't have to put that state down. You can just store it implicitly or store it on the stack or something like that. So that's about it. I just want to mention one other resource. So we have this. And then another really good example, though unfortunately it's in Go, of exactly this sort of trying to use concurrency to make a problem cleaner is this lovely video in which Rob Pike, who's a Go compiler developer and overall very smart person, talks about how they wrote part of a compiler with this technique, and it made it a little simpler. Though the fun story there is eventually they took out this technique because it was scary, and did it differently. So if you want, I can show QR codes for this, or I can somehow get these links to you guys. They'll certainly be in the description of the YouTube video recording of this. But otherwise, I've certainly taken enough of your guys' time. Okay. Thank you for attending, and I hope you got something out of it.